Hello and welcome to the second lecture on FET. So in the last lecture you have seen the introduction to FET and basic structure of JFET. So as you all know, the JFET stands for Junction Field Effect Transistor. So you have seen it, the basic construction. So let me jump to this diagram. So you all have seen the N channel JFET and P channel JFET. So the main base layer here is of N-type material in N-channel JFET, and in P-channel JFET the main base layer is P. So this you all know. So let me clear this and let me go to the new page. Select. So let us write again. So today we will discuss on the working of the JFET. So I'll take an example of N-channel JFET. Sorry, this is supposed to be an even. I'll erase this. I'll write again. Okay, so this is your P and this is your N. So base layer is N, so it is N channel JFET. So this is your source, drain and gate. So these are interconnected, so I will not write here again. So this is understood. Okay, so it is understood. So I will not write this. I will not show. So here, when you diffuse a P-type material with N-type material, always a thin layer is formed across this on either side of this diffused layer. So this layer is nothing but this is called as the depletion region is formed, because as you all know, which we have already studied in the diodes, when we combine the P-type and N-type semiconductor material, so you all know when we construct, how do we construct a diode? So when we combine a P-type material with N-type material, in between one junction is formed. So this junction is nothing but the depletion region. So likewise, when we diffuse a P-type material on N channel or N-type substrate, so here a layer is formed. So that layer is nothing but it is called as diffusion or depletion region. Sorry, not diffusion, it is called as depletion region. Let me clear this section. So on either side there is a depletion region is formed. Okay, so now let us understand the working of this. So this is, as we all know, this is drain, this is source, and this is gate. So for N channel JFET, we will connect a positive potential across the drain and negative potential across the source, and for time being the gate voltage we will keep it as 0 volts and understand the working of it. So now what happened, we have applied the external potential. So if we, before applying any potential, now suppose for example if VDS is equal to 0, then what is the current that is flowing here? The current flowing here is 0, because we have not applied any external potential. Even in the diode also, if we do not apply any external potential, there is no net flow of current, therefore the flow of current is equal to 0. So same thing is also applicable here. When you do not apply any external potential here, so there is no flow of current from source to drain. So basically in transistor you all know that this is emitter, this is base, and this is collector. So basically our intention is to make the current to flow from emitter to collector. So likewise in JFET our intention is to make the current to flow from source to drain. Okay, so now to make the current to flow from source to drain, we have to connect an external potential across the source to drain. Okay, so let me clear this all. So I'll write this here again. So this voltage we call it as VDS. So initially when VDS is equal to 0, there is no flow of current. Now let us apply the VDS. Now let us make VDS as some positive voltage. So let us consider as 1 volts. So what will happen? So this is a negative, it's connected to negative potential, and this is connected to positive potential. Now what are the majority carriers in n-type material? You all know the majority carriers are nothing but electrons. So now what happens, due to this negative potential, these electrons get repelled. So due to that, so these starts flowing on the other polarity, because here the drain is connected to the positive potential. Now due to this positive potential, the electrons get attracted, so thereby the electrons flow from source to drain. So near the source the electron get repelled, and at the drain the electrons get attracted. So thereby there is a flow of current from source to drain. Alright. So now there is a flow of current, and this channel, let me write once again one more diagram here. So this channel acts like a resistance, like this. So as you increase the flow of current, it is basic, it applies simple a basic Ohm's law. As you increase this VDS, the current also increases. As you increase the VDS, this current we call it as ID. The current which is flowing from source to drain, we call it as ID. As you know, as a simple formula, then as you increase VDS, ID is also increase. So it means as you increase the VDS from 0 to 1, 1 to 2, or 2 to 3, then current also increases. Okay, so this is the basic working principle of JFET. So now there are few concepts that we need to understand here. Let me clear the section which is not required here. Let me clear this. Let me clear this, and this. Let me clear this as well, this as well, this as well, this one. Okay. Now this is N. So we know that the majority carriers in the N channel is the electrons. So electrons are going from source to drain. Now there is some concept which come across. Now you see that if you divide this JFET into two parts or two sections, now this is P and this is N. Now the potential is negative and here it is 0, so no problem. So N is applied with negative potential. It means the P and N at this point it is forward biased, and whereas here the drain, that is nothing but this is N-type material itself, so it is connected to P. It means the P and N is reverse bias condition. So your depletion region is not evenly distributed because of this positive potential at the drain and negative potential at the source. So your depletion region looks like this. Like this. Let me write the new graph here so that you can understand. So this is your N channel. So we are diffusing the two P-type materials. So this is P, this is also P, and this is your N. So now this is your drain. Now this is your source, and the two terminals of P are shorted internally, so I am not showing that. So this is your G. So this is the gate voltage VGS. So initially we will keep it as 0 volts. So now we will apply a positive potential to the drain and negative potential to the source. So this will make the diode to be not diode. So this will make the electrons to flow from source to drain. So as I told before, so this is positive and this is negative because of the external potential. So due to which N is connected to negative, so it means it is forward biased, and P is connected here, the N on the other side is connected to positive, it means it is reverse biased. So the depletion region, what I want to tell you is the depletion region not evenly distributed. So here the width of the depletion region is more on the drain side when compared to the source side. So here the width of depletion region is narrow, whereas the width of the depletion region is more. So this is actually how the formation of depletion region of a JFET. So it looks like that. It is not even, which you have seen in the previous diagram. So now this is the VDS which we have given, 1 volt. Next we will make this VDS as 2 volts. So accordingly, as you increase the VDS here near the drain, the reverse voltage also increase. So thereby the width of the depletion region near the drain also increases. As you increase and further increase, so at some point, maybe at say 5 volts, at some point here the width of the depletion region increases such that both these junctions are come in contact close together, and then the flow of current is restricted. It means the current becomes constant. Till such point what happens, the current was gradually increasing. So if I write the graph, there is no place to write here graph, so let me write a short graph here. So this is your VDS curve, x-axis is your VDS and your y-axis is ID. So as we start the VDS with 1 volt, 0 volts, there is no flow of current. At 1 volts there is some current flowing. As we increase VDS, current also increase, ID also increase. At some point when VDS becomes too large, the width of the depletion becomes too wide, so it touches each other. So this point we call it as pinch off voltage. At that point what happens, the current becomes constant like this. So this point we call it as VP. We call it as VP, that is pinch off voltage, and this current we call it as IDSS. This current we call it as IDSS. IDSS. So I cannot write here, so I have written here. So this current is a maximum current. So this is a maximum source to drain current, saturated source to drain current. IDSS stands for saturated source to drain current. It is a maximum current that we can flow from source to drain with VGS is equal to 0. So let me revise this again. Initially, let me clear this section here. In fact, let me clear this all and write your depletion region. So this is your two p-type materials or diffused. When VGS is say 0, or sorry, this is not VGS, this is VDS. When VDS is equal to 0 volts, then you can see the width of the depletion region is evenly distributed because there is no potential difference, so it is evenly distributed. Now as you increase the VDS, what happens, that drain is on the positive potential and source is at the negative potential, then what happens, your width of the depletion region is more near the drain and it is less near the source. So this is a formation of depletion region. As you increase VDS, current also increase. As VDS increase, current increases and width of the depletion region also increase. So this path acts as the channel. That is why it is called as N channel, because electrons are flowing through this channel, so it is called as N channel. If it is P material, then it is called as P channel because holes are moving from source to drain. So basically this path acts as a channel for the flow of current from source to drain. So now I was talking about as the VDS increases, the flow of current increases. Along with the flow of current, this depletion region near the drain also increases, and at some point of as the VDS becomes very high, these both depletion region touch each other. When these touch each other, then the current get restricted. There you might ask a question, when both are come in contact, where is the place for the current to flow? Yes, the question is valid, but there is a small gap which you cannot control it. There is a constant flow of current that is occurring. So it is a simple example. Now for example, if you take a water pipe and the water is flowing at full pressure, then if you try to close that water pipe, it is very difficult to block it. Still there is a water is flowing through some corner. So likewise, though it is completely blocked, there is a constant flow of current which is flowing, because as you increase further VDS, the current will not increase, the current is saturated. As you increase VDS from say 5 volts to 6 volts, the current remains to be same. For example, the current if the maximum current is 8 milliamperes, so current remains to be constant even though you increase the VDS to 6 volts to 7 volts or 7 volts to 8 volts. So this voltage at where the current becomes constant, this we call it as VP. So VDS is equal to VP at a pinch of voltage. So VP stands for pinch of voltage. So basically this is the graph. So this is the graph which we have shown here. Now you can see as the VDS increases, the current also gradually increase, and that when both the depletion region come in contact, so what happens? So current becomes constant from there, and so this region below this increasing region we call it as a ohmic region, because the channel acts as a basic resistance. So as the Ohm's law, ohmic contacts or ohmic resistance area, as you increase the voltage, current also increases. A simple fund of Ohm's law. Now after this point, this is called as the saturation region, because the current gets saturated. As you increase the voltage, there is no flow of there is a flow of current, but it is constant. And this maximum current at this point we call it as IDSS, saturated source to drain current. So this is a basic graph of a characteristic graph of n-channel JFET with VGS is equal to 0. Okay, this is the one concept. Now let me clear this section. We will come to the second concept. Let me clear this entire window. Sorry. Let me write this JFET again. So this is n-channel JFET. These are both p-type materials which are diffused. This is N, so this source and drain. So the condition which we have taken before is for VGS is equal to 0. Now we will discuss the second condition. This is your gate, this is your source, this is your drain. Now in this case, we will connect a negative potential across this gate to source. So now what happens, since a negative potential is connected to P and a positive potential is connected to N, so what happens, this will act like a reverse biased PN junction. So due to this reverse biased PN junction, now rather than having an equally distributed depletion region, now the width of the depletion region is already increased to certain level on both the sides. Now this is your normal depletion region, you can consider with VGS equal to 0, but since I applied a VGS say with minus 1 volt, because it is of negative, so that is why we call it as minus 1 volt, because we are connected a negative potential to the gate. Now due to this negative potential across the gate, rather than having a normal width of the depletion region, now the width of the depletion region is increased due to reverse bias condition. So now due to this reverse bias condition, still we have not applied VDS, so assume VDS is equal to 0 volts. Now only the width of the depletion region increased, but there is no flow of current because we have not applied any VDS. Now let us apply VDS. Now let us apply VDS is equal to 1 volts. So when we apply VDS is equal to 1 volts, like as I said before, as you increase the VDS, the current starts flowing or linearly increasing. So now if I draw the graph here, this is your ID and this is your VDS graph. So now this is the first graph which we had written, which has become constant. So this is nothing but your IDSS, saturation current. This is the first condition is for VGS equal to 0 volts. Okay, this is the previous graph which we had written earlier. Now in this case, now VGS is equal to 1 volts. Now what will happen when VGS is equal to 1 volts? Because already there is a width of the depletion region increase. As you increase VDS from 0 to 1 volts, there is a further increase. of depletion region. Now as you increase from 1 to 2 volts, current also increases. Along with that, the depletion region also increase near the drain, because as you know, it is reverse bias due to this positive potential near the drain, and this is n-type material. So that is why there is a more depletion region near the drain side compared to the source side. So now, rather than reaching the pinch off voltage at 5 volts, now we have reached the pinch off voltage at maybe 4 volts. So if we draw the graph, rather than reaching the pinch off at 5 volts, we have reached the pinch off at 4 volts. So this is because VGS negative gate voltage, which we already applied for, minus 1 volt. It means as we increase the negative gate voltage, the current reaches the saturation at the earlier than IDSS. So now this is your saturated current. Now as I increase this VGS, say minus 1 to minus 2 volts, now it will reach the saturation to even before the earlier one. So now this is for VGS equal to minus 2 volts. Like this, if you continuously increasing VGS, it will reach to a saturation level earlier and earlier. You can consider like this. I'll write one more diagram later to make you understand in a simple concept. So this is VGS is equal to, say, minus 3 volts. Okay, and at some point when VGS is equal to minus VP, so this region we call it as cutoff region. It means the transistor is not at all on, it is transistor is off. So basically we will write like this to represent the VP. So this is the basic graph. If you see here, so I will show you this. So this is how for different VGS the graph looks like. You look at this section, don't consider this we will discuss later. This is a transfer characteristic graph. So the right side section we call it as a drain characteristic graph, and this left section we call it as the transfer characteristic graph. Okay, so now as you can see, with VGS is equal to 0, there is a maximum flow of current, and then it reaches a saturation point. Then for VGS, say less than VGS1, so minus 1 volt, so it reaches saturation at the earlier than VGS0. Then VGS2 reaches saturation earlier than the VGS1. So like that it will continue, and at some point it will become off. Means off in the sense the transistor will not at all turn on. It will remain in a on state even if I apply VDS for a high gate voltage. So this is the basic working of the transistor. So now we will wind up the session here. So in the next session we will look at the basic calculations of JFET, and we will solve few of the examples. Okay, so thank you, stay safe and take care.